Maybe you can get started. Okay, welcome everyone to this third lecture in terms of introduction to gravitational lensing. So in the first lecture, I covered some of the basics and the basic equations that go into gravitational lensing. Then yesterday you heard a little bit about strong gravitational lensing. So Anupreeta talked about the case when the alignment between the source and the lens is so perfect that you get multiple images of the same object, and how using strong gravitational lensing you can learn about like multiple different things, going from the accretion disks of black holes to cosmology as well. In principle, if you use time delays of quasars which are getting multiply lensed, or type 1a supernovae which are getting multiply lensed, then you can learn about cosmology. So she gave you a fair number of good-looking pictures. So now it's my time to do that. So this is another beautiful image. This is from the Hubble Space Telescope, where you can see many galaxies forming these galaxy clusters, all these yellow, red, and red galaxies. And then there are background galaxies which are getting stretched. So I think this is part of this dragon arc or something that I might have also shown to you. You can see these beautiful arcs here as well. There are a couple of images which look similar. Then this radial arc that you can also get multiple other features. So you can take all these strong lensing systems that you see, or strongly lensed images of the source that you can see, and try to predict where each of these positions should be. And then try to work out a model for the mass profile of the cluster, which will result in these kind of images of these sources. Okay. So it's a very complicated problem. It's a very complex problem. And it's also an inverse problem, right? It's because you don't know how exactly the initial galaxy looks like. So you have to make certain assumptions, some parametric forms, or in cases like these where you have very detailed images, then you can get like a pixelated form for your source, and then ask how the intensity in each of these pixels in the source should look like in order to produce an image like this, in addition to what the mass distribution of the cluster. And so it's a very complicated problem, and people have developed different kinds of methods. They go through something called parametric reconstructions, where they will put a mass model for this galaxy, for all the galaxies that you see in the foreground, and then try to scale it up and down to see when the observations that you see can be explained by the model. So that's the kind of thing that is done in strong lensing. But today, what we are going to talk about is something in the which is further out. Right? So we are not going to talk about these images which get like stretched in tangential directions where the magnifications are really large. But instead, we'll talk about teeny tiny galaxies which are further away from the center of this galaxy cluster. And the shapes of these galaxies also get distorted. So we'll try to see how the distorted shapes of these galaxies can be then used to also put constraints on the mass distribution. And you will say, so why is it important? If you have this strong lensing, why not just use strong lensing? So this is something that Anupreeta would have mentioned as well. If you look at any of these arcs, then the most well-constrained parameter, this strong lens, will be the mass which is contained within something called the Einstein radius of the lens. So once you know the source redshift and the lens redshift, and you have this arc, and you can roughly carry out a circle on which this arc is lying, then the mass within that circle is very well constrained. Now, if you have images at different positions, then you can constrain the mass within different kinds of circles, so you get the mass profile. But all of this phenomena of strong lensing is relatively subjected to the cluster center. So as you go further and further out, then it becomes harder to predict what the mass profile of the cluster is if you just use strong lensing. So instead, if you go to further out galaxies, which are getting only weakly distorted, then you can measure the mass profile of these clusters even out to larger area. And that's where weak lensing becomes it. Okay? So what is this weak gravitational lensing? So let me show you a cartoon picture of what happens. So there are background galaxies. See this kind of blue galaxies that you see here. And then the light coming from these background galaxies, it gets deflected due to these dark structures that you are seeing here, ghostly structures, that of dark matter. And these deflections, after the light undergoes the deflection, it comes to you, and this is what you observe on the sky. Right? So if you look at these light bundles, so initially the galaxies, the light bundles from this galaxy, they look like this. But after they undergo deflection, the light bundles, they change in their orientation. Right? So it is this change in the orientation is what we are going to measure. Okay? And the way to measure it is by looking at the shapes. Now, it would all be easy if someone told you what is the original shape of the galaxy, right? But that is not known. Okay? And so what you see is only this thing, and you have to infer what is causing the distortion. Okay? Now, so the premise that I'm going to set up is that if you look at these shapes of these galaxies, you can indeed infer something about the matter distribution. Now, weak lensing, because of this critical surface density, it is most sensitive to structure which is roughly halfway between the observer and the source. So lensing structures which are halfway between the source and the observer, they are the most efficient in order to carry out this lensing. And so what happens is, if you look at the shapes of galaxies which are really far away and observe the shapes here, then they tell you something about the matter distribution in between. Now, what you can do is, instead of looking at galaxies which are here, you look at galaxies which are somewhere here. Then they will tell you about the matter distribution, which is roughly halfway between them and you. So in this manner, you can actually make slices of the dark matter distribution and make a 3D map of the dark matter, which is present in it. Okay? So the way to do it is take galaxies at different redshifts or different distances far away from us and look at their shapes. And their shapes can tell you something about the matter distribution. And so you can then reconstruct a 3D matter distribution. So it is quite powerful because dark matter is something that you can't directly see. You have to infer it. And one way to infer it is by doing this this kind of using weak lensing, right? So you can do a tomographic reconstruction. Okay, let's get back to the equations that we were using. So this is just the general broad overview of what we are going to learn now. So some of the important equations. The first one is this equation: beta is theta minus alpha of theta. If you remember, the pretty standard geometry thing that you get. This alpha is not the deflection angle; it's the scale deflection angle. Beta is the source position if there was no lens between us and the source. Theta is the position of the image that. This is a nonlinear equation because alpha of theta is not just a linear. Alpha and theta are not related in a linear fashion. And so for a given value of beta, you can have multiple images of theta. Today, we are not going to work in that regime. We are going to work in the regime where you're only going to form single ellipses. Okay? Then, if you want to figure out what this alpha is, you need to know something called the lensing potential. So, given a surface density, you can define this thing called kappa, which is the surface density with respect to the critical density, given the source direction. And so you can write down or define this thing called the lensing potential, which is just an integral of this kappa over different positions in the sky with this kind of a curve. Then if you want to work out what is the deflection angle, then you just have to take a gradient of this lensing potential. Just like you have a potential in gravity, you take a first derivative, you get the force. So similarly, same relation, deflection and the lensing potential. Just that this is a 2D gradient. Remember, alpha is a vector, and that's why you take a gradient and you get a vector. Then, what is the relation between kappa and psi? If you take the Laplacian of psi, you get 2 times kappa. Now, this is something, again, you can derive mathematically, and I would encourage you to do that. You take a Laplacian of this, you will start to get a 2 times the delta function. So that's something that we should try to do. And then there's this thing called shear. So this defines something called a convergence, this kappa. But in addition, there's something called shear as well. This comes from the linearization of how small changes in beta reflect into changes in theta, the image positions. And we have talked about something called the magnification matrix that comes in, which looks something like this. And so there are these terms gamma 1 and gamma 2, which enter this magnification matrix. And this gamma 1 and gamma 2 again are related to the lensing potential in this particular. Okay?
Are there partial derivatives?
I'm sorry?
Are there partial derivatives?
Yeah, so all these are partial derivatives. So del psi by del theta 1 is del psi by del theta 2, del theta 2. And this one is del psi by del theta 1, del theta 2. So the way you get this is by doing a partial derivative of beta with respect to theta. Beta is a vector, theta is a vector, so with 2 components each, and so you get 4 components. And those are these 4. So you start from this vector equation, you take a derivative, you will end up. Okay, so this magnification matrix, again, this is a review of what we have done before. You can decompose it into a convergence part, which looks like 1 minus kappa times an identity, which means that if you did not have gamma 1 or gamma 2 was exactly equal to 0, what will happen is if you take circular sources, they will just remain circular sources in the image plane. It's just that their radius will increase or decrease, depending upon the value of kappa. But if you have a shear, what it does, it changes these circular sources into something which looks like an ellipse. So we have a convergence which just changes the size of this circle, and then the shear, if you add in the convergence and the shear, then you get something. What this angle is of the major axis with respect to, say, the x-axis, that is something that we'll get to. That angle is related to the values of this gamma. So we will look at what that is. So circular sources, as I said, they become elliptical. An ellipse has 2 quantities that you need to specify. One is the direction, and the other one is how elliptical it becomes. Okay? And so these 2 quantities should be related to the gamma 1 and gamma 2 that we have. So it turns out that it is easy if you think of this gamma as a complex number. There is nothing complex about the shear. It's just that there are 2 numbers. You want to keep them separate, so you call one of them a real part, the other one imaginary part. There is nothing imaginary about this. So it just makes the mathematics simpler if you think about it in this stuff. So then what you can do is you can ask, okay, so if I have this gamma which is equal to gamma 1 plus I gamma 2, how are my axis ratios that I see for this new ellipse, how are they related to these numbers, kappa, gamma 1, and gamma 2? So for that, what you need to do is you take the magnification matrix that we had and you try to diagonalize. Because when you diagonalize it, you get the eigenvectors and the eigenvalues. The eigenvectors will tell you these directions, and the eigenvalues will tell you how much stretch the source becomes in this direction and in this. Okay? So if you take that particular magnification matrix, this one, and you try to diagonalize it, you will notice that the determinant of this matrix minus lambda times I, if you set it to 0, then the eigenvalues that you get, they are of this particular form. So you get an equation which looks like 1 minus kappa. So let's see. Maybe I should just do it. Let's see. Minus gamma 1, and then this minus gamma 2, minus gamma 2, and minus kappa plus 1. And so what I'm going to do is take this matrix, which is A minus lambda times the identity matrix, and the determinant of this I will set it to 0. So what I have to do is just do a minus lambda here, minus lambda, okay? And take the determinant and set it to 0. So what I'm going to get is 1 minus kappa minus gamma 1 minus lambda times this 1 minus kappa plus gamma 1 minus lambda, and then minus gamma 2 square equal to 0. Okay? And so again, this is 1 minus kappa minus lambda, so 1 minus kappa minus lambda the whole square minus gamma 1 square, right? Because this is like, this is of the form A minus gamma 1, and this A plus gamma 1, so that's why I can write it like this, right? And minus gamma 2 square equal to 0. And now this you can solve, because this gamma 1 square plus gamma 2 square, remember if I define my shear to be gamma 1 plus I gamma 2, gamma 1 square plus gamma 2 square, it becomes the modulus of gamma square. And so this thing, I can just write it down as mod gamma. And this modulus is just now the modulus of gamma 1 plus I gamma. Now from here, I can solve for lambda, because I take it here, then I take a square root, it becomes plus minus mod gamma, right? And so you will get that lambda is equal to 1 minus kappa plus mod gamma or minus mod gamma. So these will be the two eigenvalues. So that's exactly what is written here. So the two eigenvalues that you get are basically 1 minus kappa plus mod gamma and 1 minus kappa minus mod gamma. So the sizes of or the semi-major axis and the semi-minor axis of these ellipses, if your size of the original source was R, then the image, they will have these kind of semi-major axis, which is R divided by 1 minus kappa plus mod gamma. And then the minor axis will be something. And so now once you have these quantities, now you can see how the gamma is related to these major and minor axes. Now, conventionally, it is easier to take 1 minus kappa out of this denominator, so that you get R divided by 1 minus kappa times 1 plus mod gamma, and then 1 minus kappa times 1 minus mod G. This G is called a reduced shear. And this reduced shear is just gamma divided by 1 minus kappa. So this is just definition change. I'm just doing some arithmetic. So now what you can show is that this mod G is just 1 minus B over A divided by 1 plus B over A, where B over A is the axis ratio. Okay? So if you take the axis ratios, you have to divide this by this. And so that's B by A. And so you will get this R and 1 minus kappa, all these things will cancel. You'll just remain with this 1 plus mod g and 1 minus mod g. You rearrange it and you get what mod g looks. So mod g will just look like 1 minus b by a divided by 1 plus. And equivalently, b by a will be this, which you can see. Okay? Okay, so axis ratios of these background galaxies, they can tell you something about this reduced shear. So, as I told you, you observe the shape of the galaxy. If the galaxy was circular, then its shape will directly tell you what is the reduced shear at the location of it, okay? in the lens plane. Okay? So this is one way that you can see that you can use the shapes of galaxies directly. You don't even have to have multiple images. Even if you have a single image of a galaxy, if you knew it was circular, then this you can. Okay? Of course, galaxies are not circular, so we'll come to what happens later.
Then how do we know what its original shape? Circular.
Right. So I will tell you that it's not important. And like if you had only a single galaxy, it would be difficult to do it. But if you have multiple galaxies, then the individual shapes of these galaxies are not that important. What is important is that all these galaxies are being lensed by the same structure. And so if you average out the shapes of these galaxies, the intrinsic shapes will cancel out because one will be like this, another will be like this, third one like this. What remains is only the coherent shear that gets imprinted on these galaxies. We'll come to it. But we talked about the eigenvalues. Now we can talk about the eigenvectors so that we will understand what is this direction. And so in order to get the eigenvectors of this matrix, what you need to do is take the matrix and multiply it by a vector. You should get the eigenvalue times the same vector. Right? This is the definition of how you get eigenvalues and eigenvectors. So what I've done is here I've defined 1 comma tan phi as my vector. Right? So this is, if this is phi, then 1 comma tan phi is a line which goes like this. And so what I'm trying to figure out is if that is the vector, can I find out the relation between gamma 1s and gamma 2s and this phi? So in order to do that, I just have to write down this particular equation and then try to solve it. So if you just write 1 minus kappa minus gamma 1 minus gamma 2 tan phi, it should be 1 minus kappa plus this mod gamma. You rearrange this, you will get that tan to phi will be equal to gamma 2 divided by gamma. So you take this equation, you get a tan phi. You go from tan phi to tan 2 phi using the normal relation that you are used to in geometry, and you can show that this tan 2 phi is gamma 2 divided. Which means that if I tell you gamma 1 and gamma 2, you can tell me exactly at what angle a circular galaxy's shape or image will appear. Okay? A galaxy which is circular, it undergoes a shear pattern which has this gamma 1 and gamma 2. Along what axis will the measure axis of this galaxy will be oriented in its image? You can know if you know gamma 1. On the other hand, if you know that if you know the shape of that galaxy, you see a major axis, then you know what is the angle of the shear at that location. Okay? What is shear related to? Shear is related to the mass distribution in the lens, and so you learn about the lens distribution. Okay? Clear? Now, let's these gamma 1 and gamma 2s are quite funny, and so you're not used to, like, you may think about them as vectors, but they are not really vectors. And that's why I wanted to show you or give you a feeling of what is gamma 1 being positive or negative. Okay? So if gamma 1 is positive and gamma 2 is 0, then it means that your ellipse looks something like this. It's horizontally shaped ellipse. Okay? Instead, if your gamma 1 is negative but gamma 2 is 0, then still your ellipse the major axis and the minor axis are along x and y. It's just that the major axis is along y axis. So this is a little bit counterintuitive because typically you would think gamma 1 is 0 means it will be like this. Gamma 2 or gamma 1 is positive means it will be along the x-axis. Gamma 1 or gamma 2 which is positive will be along the y-axis, but that is not. Okay? So both of these have gamma 2 exactly equal to 0. One of them has gamma 1 greater than 0, gamma 1 less than 0. Okay? It's important to remember. And what about the other case when gamma 1 is equal to 0? So if gamma 1 is equal to 0, while gamma 2 are greater than 0 or less than 0, then they get oriented at 45 degrees. And this is happening because of this tan 2 phi thing. Once you have 45 degrees, tan of 90 becomes infinite, and so this gamma 1 will be 0 in that case. Okay? So when gamma 1 is 0, your galaxies have to be oriented at 45-degree angle with respect to your x-axis. So this is something to remember. It's a little bit different from the normal vectors that we use. So here is an image which shows gamma 1 on this axis, gamma 2 on this axis, just to give you a visual representation of how the galaxy shapes will look like for different values of gamma 1 and 2. So when gamma 2 is equal to 0, you can see that all these things, the major and minor axes, are aligned either along x or y. If along x, then gamma 1 is positive. If along y, the major axis is along y, then gamma 1 is negative. You have a question?
Oh, yeah.
Yes.
All those galaxies, like in respect of where they are behind the source, all of them would look like this shape.
So, as long as they are undergoing some lensing, there is a shear at a particular location, then circular galaxies will transform to this, to ellipses.
But irrespective of where they are, the location.
Yes, it depends upon, so the shear at any given location will depend upon what the mass distribution near that location.
The shear would differ from location.
Shear will differ from location. Okay? Okay, good. So then, let me show you in visual terms as to what exactly happens, right? So let's consider all these galaxies which are here on the left-hand panel, which are all circular, okay? For simplicity. Now, there is no lens in between them and us. Now what I'll do is I'll put a lens which is in between these green galaxies and us, somewhere at the center of this image. When you do that, you start to see that all of these galaxies, now their images start to become distorted. And the distortions are such that you see this particular pattern arising. So first of all, if you go away from the center, the distortions become smaller and smaller. That's the first thing to notice. Second thing, these ellipticities that you see, they are all tangentially oriented. Just like your arcs were tangentially oriented. Now you are not seeing like big long arcs. Instead of that, your galaxies are just getting stretched in tangential direction. If you have an axially symmetric mask which you put here, then this is what. So this pattern is something that you can use in order to learn about the mass distribution. So what you have to map is how these ellipticities change as a function of distance away from the center. And that can tell you something about the mass distribution, the whole mass profile of this object which is causing the lens. So the obvious question, all galaxies are not circular. So let's modify this pattern. So now the unlensed population, I've put in some kind of random ellipticities on top of these populations. And then again you put in a lens in front of it. Then what do the distortions look? So they look like something like this. Now you can see individual galaxies if you take, so for example this particular galaxy, you see that it is oriented like this, it became a little bit fatter, right, in this direction, because lensing is tangentially distorted. But its shape is now like this because a lot of it is actually dominated by what its intrinsic shape is. But still, coherently, if you look at this image, you can pick up a pattern that there is some tangential distortion which is happening on average to galaxies which are separated at a distance r from. Okay? So even if these galaxies are intrinsically randomly oriented, now what you do is you go here and you draw a circle. Say you draw one circle here, another circle. You take all the galaxies which are at say certain radius r, and you average out their ellipticities. When you take the average of these ellipticities, the ellipticity that you observe is composed of two things. One is the intrinsic ellipticity of the galaxy, and the other one is the shear which is imprinted on it because of gravitational lensing. So when you average many such galaxies, the intrinsic shapes of these galaxies will turn out to be zero when you average it, not individually, just because there is no particular orientation in the universe, right? And so you will average it out to zero. And then what remains is these coherent distortions which were imprinted on these galaxies because of the lensing of okay? And so you take these coherent distortions and then you figure out what the shear is at a distance away or at a distance radius r away from this particular place. Okay? The other way you can do it is also you can pixelize this whole grid. And you can take pixels here, you can take galaxies here, you can take galaxies here, and so on. In each of these pixels, you average the shape of those galaxies. Then you get some tangential distortion at that location. You do the same for this pixel, and so on, so that you can get a shear. The more galaxies that you average, the noise due to the intrinsic shapes will go down. Because if you have 100 galaxies with random orientation, they will not exactly give you zero. They will statistically give you zero, plus minus some number. But how big that deviation is from zero will be determined by how many galaxies you start. So if you have a larger number, the better your. Okay, good. So once you do that, then you can learn about the mass distribution, right? So now let's try to go to here shapes of galaxies to understand how you actually measure the shapes. So I'm going to show you a beautiful image first, and then maybe we will also see how galaxies that we use in order to do weak lensing actually look. And they will not look as high signal to noise ratio as these things. Okay? But just to set the stage, this is a galaxy. I want to measure its shape. So what will I do? The first thing to do is to find out what is the centroid of this galaxy. How do you do that? In order to identify the centroid, you take the surface brightness distribution of this galaxy, and then you calculate the first moment of this surface brightness distribution. So the first moment will tell you what is the location of the center of this galaxy. See, this is a vector, so theta bar is d2 theta I theta times theta divided by the normalization factor. What is this Q of I? This Q of I is just some kind of a weighting, because you know that the measurements will be more accurate at the center where you are receiving many photons, while as you go further and further away, the noise will increase. And so you don't want to just carry out a moment which is not weighted. Okay? So if you weight the distribution while calculating these moments, then you will get a better estimate of this centroid. And so that's what you try to do. Okay, so that's what this Q is. Once you know the centroid, you know exactly the location where this galaxy is centered. Now you want to calculate the shape. So if the galaxy was a Gaussian, then what you can do is you can take a second moment of this distribution and then figure out what are the sigmas of this Gaussian by looking at the second. So that's exactly what you do. This is a Qij, which is the second moment. So you again take a d2 theta I theta. So you're summing over all these pixels at different intensities in each of these pixels. And then you're taking the second moment. But while taking the second moment, you do this reduced second moment. So theta I minus theta I bar and theta j minus theta j. So along each of the axes, theta 1 axis and theta 2 axis, you can calculate these moments. So now you get again a 2 by 2 matrix, right? Because this I and j can be 1, 2, right? And so you get basically 4 different elements using this matrix. So just to simplify things, you can think about it as the d2 theta I of theta. Let's consider I of theta to be a Gaussian. Okay? And let's suppose that this theta I bar and theta j bar, you use your coordinates such that everything is centered at 0. So then theta I bar and theta j bar. So overall space. Right? So if you do x squared times the Gaussian integrated overall space, you get sigma square of that Gaussian. Right? So if your Gaussian was a 2D Gaussian, sigma x square and sigma y square in the denominator, then if you use a x square here, then you only get sigma x square. If you use a y square here, you will get a sigma y square. Okay. So it's simple mathematics like this that you can use in order to show that indeed this is the second moment, and it will tell you something about the size of this Gaussian if you just assume that your galaxies are Gaussian. Good. So once you have this, then you can define this Qij. Now, the point is you can define now an ellipticity for the galaxy. Again, remember, ellipticity has 2 different components, right? One is how much elliptical you are and what is the angle. So similar to how we defined our gamma in terms of a complex number with 2 quantities, gamma 1 and gamma 2, we can define ellipticity also as a complex number. So one way to define this ellipticity is like this, where you do q11 minus q22 plus 2i q12 divided by this denominator that you see here. You will say why this particular definition, because this looks very arbitrary. So you can show that if your axes are, say, aligned along the x and y axis, then the modulus of this ellipticity will actually give you 1 minus the axis ratio divided by 1 plus axis ratio. This is very similar to what the shear or what shear is going to be. Right? If you remember, we had derived what this mod g or the reduced shear was going to be. It was 1 minus axis ratio divided by 1 plus axis ratio. So if you take this quantity and take a modulus of it, then it becomes 1 minus 1 by 1. So let's look at it for a simple case where we have axis aligned along the x and y axis. You can show this for a general case. Yes.
We wanted this, so we defined it that way.
Yes, yes. And there are other definitions as well, so I will show you for this. So first, let's see that it indeed reduces to this. So let's suppose your Q11, so everything is aligned along x and y axis. So Q11 will give you a square. Let's assume the galaxy is also Gaussian. So it's like sigma x square. My sigma x, I call it a. So it's a square. Then Q22 will be b square, the sigma along the y axis. So b square. So a square minus b square. If your galaxy is aligned along the x and y axis, and if you do an integral over, like you multiply x and y, and you do an integral over the Gaussian, you will get exactly 0. Because integral of the Gaussian just x, my centroiding is at 0, and so you get the mean to be exactly equal to 0. Right? So Q12 will be 0. This will just be a square minus b square. Now you can see this is a square minus b square. What is this quantity? This is a square plus b square plus 2ab. So this becomes a plus b the whole square in the denominator, while the numerator is a minus b times a plus b. So what you end up with is a minus b divided by a plus b. You divide by a and you get 1 minus b by a divided by 1. And you can see that the modulus of this ellipticity vector, in the simple case when everything is aligned, indeed gives you this kind of 1 minus axis ratio divided by 1 plus axis ratio. Okay? There are other ways of defining this, and do I have it? Sorry, I don't have it. So there are other ways of defining this, in which is called something called a distortion, in which it looks like 1 minus r square divided by. But it's a definition thing. You can define it in either ways. It does not matter. As long as you figure out how the ellipticity that you define, how it relates to the shear. We know that the shear is related to this quantity. And so if you are doing 1 minus r square divided by 1 plus r square, you have to figure out how the shear relates to that. That's okay. So since galaxies have intrinsic electricity and if they're randomly oriented, we can do the averaging. And once you do the averaging, you can show that the expectation value of the average of this electricity, it turns out to be shear if the shear is quite small compared to that. In the weak lensing regime, you are always in this particular case. And so your average of the average of the observed electricities that you get turns out to be the shear. And so you can use the shapes of these galaxies to get the shear at any given location. So we started from the shapes of galaxies, we came to the shear. Now you have a shear field. How do I use this shear? Is the question. Now, how can it tell us something about the mass distribution? So that's going to be the next part. So if you have a shear distribution, then I'm going to tell you how to get a map of the matter distribution which is causing this shear. So that's the next. So remember, we had this our lensing potential. It again becomes very simple if you work in lensing potential. Okay? That is the reason why we decided to use this kind of plan. So let's suppose someone has given me a lensing potential as a function of theta on the sky. Okay, this is, mind you, what we want to define. Okay? But let's assume that this is given. So if this is given, I can define a Fourier analog of it, or psi of n. Okay? So instead of psi of theta, now in 2 dimensions I have psi of n. This L vector is just like a k vector in Fourier space. It will have here 2 components because my theta had 2 components, theta 1, theta 2. So L has L1. Good. Now, if you remember the relation between psi and kappa, which is what we are after, these 2 things are related by the Poisson equation. So you take the Laplacian of psi, it gives you 2 times kappa. So you take this, when you take the Laplacian, it becomes very simple. It becomes mod L square times psi of L is minus 2 times kappa. So now this Laplacian simplifies in Fourier space. So that's the reason why we are taking. So this is clear, right? Now the definitions of our shape. Gamma 1 and gamma 2, they were defined like this. Again, taking these derivatives in Fourier space is easy. And so psi 1 1 will give you a L1 square. Psi 2 2 will give you L2 square. Okay? So gamma 1 is half L1 square minus L2 square. Okay, let me see. What did I do? Gamma is gamma 1. Oh, right, yes. So we started with psi, right? So it is L1 square minus L2 square times the psi of it. There is also a minus sign which comes because you take 2 times the derivative because of this I. So it becomes I square and so it becomes. So that minus 1 is here. L1 square minus L2 square and then times this psi. And then gamma 2 is psi 1 2. So that's why it is L1 times L2 times psi. And so you get this particular equation for what the shear is. Okay? So the shear now is related to the potential, and here the potential is related to kappa. So what I can do is I can use this equation in order to relate the shear and the kappa. Kappa is, mind you, again the surface density which we are after. Shear is something we can do. And so now I substitute. So for this psi of n is minus 2 kappa divided by mod L square. And so these factors of 2 and so on, they get rearranged according to this particular equation. So now you get a direct relation between kappa and gamma, which looks something like this in Fourier space. Okay? So now our job is very simple. I can measure the shapes of galaxies. I can figure out what the shear field looks like. I can take the Fourier transform of the shear field. I get gamma of L. I multiply by this kernel. I get kappa of L. Fourier transform back. I get kappa of T. So from the observed shears, now I'm getting what is the surface density with respect to the critical density. in the lens field just by looking at the shapes of these galaxies. Okay? Does that make sense? So these equations, then you can also write it down in terms of like theta vectors and so on. I won't go into the details of it. You can show that this shear is related to the kappa with this kind of a kernel. The kernel looks like this. And on the other hand, kappa is related to the shear with a similar looking kernel, which goes how to go from kappa to gamma and gamma. Okay? Easiest to look at it in Fourier space. If you want to do it, you can also do it in real space. I made him work out because he's working on gravitational lensing to make sure that he can derive this. But it is fairly straightforward, even though algebraically it can be cumbersome at times. But you can show indeed that these equations. Okay. And you can again see, so this particular thing is a vector, right? So there is some component plus I times some other component. So the gamma that you get will also be a vector. While in this case, there is a dot product, and that's why you get a scalar quantity. So you will have to show this, and it is fairly straightforward to do. It's just we don't have time to go over it. Okay, good. So then there are other things that you can do, which are also interesting, rather than doing just like full mass maps. So doing mass maps is one way, but there are other ways that you can also approach this problem. So if you look at this here, it is not a vector, as I said. It is a polar. It has two components. Rotation by 180 degrees results in the same ellipticity, right? Because if you take something which is oriented like this, you rotate it by 180 to get the same exact shape. So what you can do is you can define for these ellipticities, you always have to define some coordinate system, right? So in previous cases, we had defined the coordinate system to be like your x and y axis. So instead of that, it becomes useful if you define coordinate systems which are very relevant to the problem that you have at. Okay? So let's suppose you have a lens which is here, you have galaxies which are distributed around this, background galaxies, and you want to measure their shapes. You know that the distortions that are imprinted, if this they are oriented in the tangential directions. So it becomes easier if you define the shapes of these galaxies in a frame which has a basis, which is a radial vector and a tangential axis. Sorry, a radial axis and a tangential axis. So for this galaxy, for example, you can measure the ellipticity of this galaxy in a basis which looks like this, a tangential and a radial. Okay. Similarly, for this galaxy, you can define your x and y axis to be like this, a tangential x-axis and a radial y-axis. Similarly for this, a tangential axis and a radial axis. Okay? So if you do that, calculations simplify. So that's the reason to do it. So you can show that this gamma tangential, if you are at an angle phi with respect to the x-axis, okay, so this kind of a galaxy, you can calculate what is the gamma with respect to this new coordinate system, gamma t and gamma cross. Okay? So gamma 1 and gamma 2 that you had, you can express it in terms of gamma t, gamma cross is just a change of basis. Okay? Change of frame. Then, if this frame is oriented with this tangential like factors phi, then it turns out that you can take your gamma 1 plus I gamma 2, this imaginary vector that you have, or imaginary number that you have, or complex number that you have, you multiply it by e to the minus 2I phi, and you take minus of the real component of this, then you get the gamma in the tangential direction. So you can show this. It's a simple change of. Similarly, this gamma cross will now be 45 degrees with respect to this tangential direction. So that you can show is the minus of the imaginary part of gamma times e to the minus 2. So this tells you how to go from a gamma 1, gamma 2 that you have measured to a tangential shear component. Remember, we wanted to get this tangential shear which is imprinted at a radius r. So now, if you know this gamma t, now you can do a simple average of this gamma. You don't have to worry about, well, my gammas are vectors, so I need to do the averaging properly. Instead of that, you can just average this gamma t along this circle to figure out what is the tangential distortion that has happened on these galaxies because of this mass distribution and ascent. Now, this turns out to be very useful, and you can show that for an azimuthally symmetric distribution of matter, you can show that when you take the average of this tangential distribution at a particular distance theta, then it is related to the convergence like this. So what are these two quantities? It is the average of the convergence within theta. So let's suppose, let's go back. Let's suppose the angle between here and here is theta. Okay, it's not the angle with respect to the x-axis. That is phi. So that angle is in the plane of the star. What we are talking about is the angle between the lens, us, and the image vector. Right? So this angle is theta. So you take all the surface density which is within this theta and you average over this entire circle. Okay? So that is average kappa at theta. So this is this thing. This averaging is within the entire circle minus the surface density at that theta. So whatever is the surface density at this on this circle, that's what the second term is. So the first term is the surface density inside this circle, average, and the second term is the surface density on this. So if you can measure this gamma t, you can show that it is related to this kappas in this fashion. Okay? This is for azimuthally symmetric distributions of matter. But you can also show, even if your mass distribution is not azimuthally symmetric, you can show that if you take the average of this gamma t over this entire circle, okay? So when you have a symmetric mass distribution, the gamma t here, here, all of that should be exactly equal because it's azimuthally symmetric. But even if you don't have azimuthal symmetry, you can calculate the tangential shear here, and do an average. That average is related still to the average kappa less than theta and the average of kappa again over that circle that you have. Okay. So previously in azimuthally symmetric case, this is exactly the same, right, for all phi. So it doesn't matter. That's why there is no phi. Okay. But when you are not in azimuthally symmetric distributions, you can show nevertheless that if you take that kappa theta phi and you average over the phi distribution at a particular distance theta, okay, take that number and you have to subtract it from this number, then you get the average here. So now this is very powerful, right? Because now we are not relying on any mass distribution model or anything. We are not relying on any symmetry, right? Directly we are saying that if I will measure on tangential shear average around circles, I can get information about what is the mass contained within these circles and how it is distributed, in particular these quantities. So this is very fundamental in order to derive things like the mass profile of clusters, because you can go to galaxy clusters like this here, you can measure and start averaging over these shears to get what this tangential shear is. And then you can parametrically model this cluster and figure out what are the parameters which will result in the tangential shear that you see. So that allows you to get the mass profiles of clusters, the mass profiles of galaxy groups, in order to figure out what are the scaling relations between galaxy groups and their observables and so on. So this becomes very powerful. So I talked about two things. One is how to get mass maps. That is completely parameter free. This one, it at least tells you how to get average kappa less than theta minus this kappa average on surface. Okay? So once you have these quantities, they are related to the mass distribution, and that's why you can figure out what the mass distribution is. Okay? Yes. So the center, for example, you can, it does not matter. You can choose any center and you go around in circles. This will still apply. This is a result of using the divergence theorem. Again, in my more detailed lecture notes, it's also derived, but here it is. But I can send you again. I forgot to send you those links, but I will send you. I will get the email addresses from Vedeli and then send it. Okay, now let me show you the real world. Of course, it's quite dirty. So when you take images of the sky, you are using CCDs to take the images, just like the CCDs you have on your smartphone. So it's similar. Now, if you have CCDs, you manufacture silicon wafers which are so big in single quantity. So instead, what they do is they manufacture single wafers which are smaller, and then they butt them together in order to form a big camera. So big astronomical camera never have just one single chip. They will have many chips. So here, for example, you can see an image from CFHT MegaCam. So this is the Canada France Hawaii telescope, and it has an imager called MegaCam on it. And this is these are some of the chips on this map. So now this is an image taken with MegaCam, and you can see all sorts of dirty features. First of all these chips you can see that they have different gains, and so you start to see that even if the sky is similar, it will look quite non-uniform because of this. Then there are many dirty things like some columns are completely missing. Then there are stars which cause like saturations and trails. Here there's another star which causes saturation, some bad columns, bad rows, and whatnot. So it's complicated, right? And so you have to deal with all these things. So bad CCD columns, saturation of stars, bleeding that happens, CCD sensitivity variations that you can see. Sometimes there are satellites which go. So you are observing something and then there is a satellite which goes. I don't know if you have seen satellites in the evening sky. They appear like stars which are quite fascinating to observe for the first time. And then people like Elon Musk, they have released all these Starlink constellation of satellites. So instead of seeing just one thing go by, there's like a constellation of satellites passing by. So that corrupts your image because they are so bright that they leave a trail, a satellite trail. Now imagine many satellites going through, and you are trying to measure the shapes of these galaxies. Right? So it's pretty bad. It can get pretty bad. That's what is happening right. So there are satellite trails that you have to deal with. Sometimes there are asteroids which come in between and move and so on. So that causes problems. Then there are chip gaps. So these chips, they are not necessarily going to, sometimes they leave like gaps in the sky that they observe. So you will have a sky which is completely missing. And so that's something that you have to deal with. And then oftentimes when you expose for a long amount of time, you will also have cosmic rays which will hit your detector. And so once they hit your detector, they cause again some features to be imprinted on it. So you have to again deal with all these things. And then of course, sometimes your pixels just die. And so you can't do anything. Then as you observe in longer and longer wavelengths, sometimes there are fringing effects. Okay, so there is a CCD, and then light falls on top of your CCD. Part of the light keeps on going down, it does not get fully absorbed. It reflects from the back of your CCD and it starts interfering with the incoming light. Okay? So that causes all sorts of fringing patterns. This happens when your wavelength is larger. And so you can see all these kind of weird effects start to occur in your So you have to go through a lot of things in order to first go from those raw images that you take all this fringing and so on, in order to reduce the data to look something like this. Okay? So these are single frame images, which means I have just observed at one particular time, exposed my camera for a certain amount of seconds. Okay? And then you have to reduce all these images in order to remove all these sensitivity differences, chip gaps on the trails and whatnot. And you get an image which looks like this. Chip gaps, there is another way. So I'll come to it. Okay. So once you have this one image, now you can see many different objects here. Some of these will be stars, some of them will be galaxies. And then because you have chip gaps, so let's suppose this is one image from Megalhan, and then this is different image from Megalhan. What you do to deal with chip gaps is you take one image and the second image you take, which is slightly dithered position. So now what happens is that the chip gaps move to a slightly different position. And because of this, now you have some data here, and you have data here from the first image. So what you can do is you can effectively take many multiple dithers in order to fill out all these gaps. Okay? And then you try to stack all these. Now, stacking is also a complicated process, right? Because when telescopes point at something, if you tell it, okay, point to this particular star, it cannot do that with a sub-arc-second accuracy. Right? So it will just do it roughly in the right field of view. It won't do it with sub-arc-second accuracy unless you make sure that you are aligning your telescope to a particular target and the center has to fall on something. But that takes a lot of time. So when you are doing these large surveys, you just point a telescope, tell the telescope roughly look at this direction. And so what happens is your pixels that will be there, you will not know exactly what the location at which you are pointing. Plus, you cannot align such that each pixel will lie on top of another pixel from this particular second image. Okay? And so what you have to do is you have to define some sort of a input pixel grid that you have from the original image, and then you define something called an output pixel grid, which is a common grid onto which you want to map all your images so that it becomes easy to see. Okay? And so what you do is you take this input pixel grid and take this output pixel grid. Now redivide all these photons that you got in this year, in this pixel, onto this output pixel. Once you have done this, then you have for each image the flux that you would expect in this output pixel. Once you have that, you do this for multiple images. Now it becomes easy to stack, because now you can directly sum the flux coming in this pixel, the other pixel, and the other images. The reason why I have shown a rotation as well here is again because your CCDs, there are all sorts of distortions that happen in the image. So again, I don't know if you have this experience. If you take a camera and you are taking a wide picture, because there are so many people that are around you and you are taking a picture, people who are at the edges, you will start to see that their images get slightly distorted. So these are camera distortions which are. So you also have to correct for these camera distortions. So there are lots of complicated things that have to go before you actually get images on which you can measure shapes. Okay? And then shape measurement is another different story. Okay? So let me show you what the galaxies for which we measure shapes look like. Okay? The images that you are used to are these beautiful, succulent-looking galaxies where really you can see some of these spiral arms and whatnot. Okay? So this is the original image. I take this image, I apply some lensing shear with modulus 0.2 and in some direction, and this looks now like this. So this is how the galaxy would look like if you had an infinite resolution and you were above that. Now, of course, we have the atmosphere, otherwise we would not exist. So this very useful thing called atmosphere, it just makes things look like this. So it blurs things out. So now these beautiful looking things, they look like this. Now we have to detect these galaxies, which means we have to have a detector which will have some pixels. So from the atmospheric blurring, then you have to go to detector pixelization. After you pixelate it, then you have to also think about the noise that has to be there. Because the detectors, when they read out, they don't read out exactly what is there, but there will be a noise as well. And so you get some galaxy which will look like this. And this is still a fairly high signal to noise ratio galaxy. We have to use galaxies which are insignificant. But once you use this, you can actually learn a lot. And so let me show you one of the examples in which I am involved. I will go through this quickly, hopefully. So there are a large number of large area deep imaging surveys which are currently ongoing. I'm part of the Subaru Hypersuprancan survey. The Subaru telescope is an 8-meter class telescope situated in Mauna Kea in Hawaii. So it's basically an island in the Pacific Ocean. If you have not heard about it, it's very beautiful. But in the remotest part of this island, there's a big mountain, and on top of that mountain, about 4.2 kilometers above the sea level, is this particular telescope. This telescope has a camera on top of it at the prime focus of this telescope. So if you have seen a telescope, there are spiders on the telescope which hold a secondary mirror. In this, and the secondary mirrors are usually very small, right? So it's less big. But in this case, we put a whole camera here at the prime focus. This allows us to have a wide view. And so this camera, it looks very small here. There is actually a multi-ton instrument. So you have to think about how much engineering has to go in order to hold this instrument on top of that telescope. So using this telescope, we are doing some of these surveys. There are other surveys which have now completed. In fact, all these three surveys are completed: kilo degree survey and the dark energy survey. One of them is being run from Europe. The dark energy survey primarily run from US. And this one is a collaboration between Japan, Taiwan, and Princeton. There are also many other surveys which are planned for future, so it would be useful for you. The legacy survey of space and time, which will be done using the Vera Rubin Observatory, which you can see here. It's another large scale observatory which will actually blow all of these surveys out of business. So this is going to come up within the next year or year and a half or so. So very relevant if you decide to do your PhDs. Then there is Euclid mission, which is going to be launched soonish. UVA is going to be part of it soon, and we used to Leiden. And then so that is from the European side. And then WFIRST, which is now called the Roman telescope, is going to be launched from US. Okay? So this is an infrared observatory which will be launched in space, and again it will carry out parts. So with the hypersuprancan survey, we have mapped out a large portion of the sky. This is roughly 1 year of data, 100 square degrees, 140 square degrees. So in different regions, so this shows the RA deck distribution of the galaxies. And you can see the scene distribution here. It shows you how good our data quality is. Okay? So the scene, which is how much the atmosphere is blurring your images, the scene that we had, the median scene was about 0.6 arcs. So you need very good seeing in order to run good imaging, good beat lensing survey, because you want minimal blurring. If the blurring is minimal, then it becomes easier to read. Right? And so that's the reason why HSC is quite interesting. So with this HSC, let me show you quickly what we have done. So we talked about mass mapping. So I'm going to show you an example of this. So we took one of these fields here. I don't remember which one this was. And then for that particular field, I don't know if it is easy to see at the back or not, but there are some whisker plots that are shown. Okay? So these whisker plots are telling you what is the shear at any given location on the sky. Okay? So what is a whisker plot? There is a white line that is present in this image in the top panel. And that white line has a magnitude and a direction. The magnitude or how long that line is tells you what is the shear at that location, and the direction tells you the direction of that shear. How did we get that? We took some galaxies which are very far away. We averaged their shades in different pixels. So at this pixel, at this pixel, at this pixel, and so on. And so we get a map of the shear from the galaxy shapes that we are. So that map of the shear are the white lines that you see. Okay? Very far away galaxies. Then intermediate distance galaxies, we do the repeat the same experiment. And again, even further closer to us, galaxies, we repeat the same experiment. And these are galaxies which are even closer to us. We repeat the same experiment. Okay? So this gives a shear field at these four different, for galaxies at these four different locations. From the shear field, you do the Fourier transform, multiply by the kernel, you get kappa. You take the kappa, you take the Fourier transform of it, you get kappa as a function of theta. So the surface density as a function of theta of matter, which is causing the lensing of these galaxies, is shown in blue and white and black that you see. So white means really overdense regions. Black means underdense regions, something like whites. Okay, blue is intermediate. And you can see that when we looked at galaxies which were really far away, we are doing a tomographic reconstruction of matter. And so galaxies which are very far away, they tell you something about matter roughly halfway between them and us. Then here again, halfway between these intermediate galaxies and us. And then again, some nearer galaxies and then further nearer. So now we can make a 3D dark matter. Now, one of the things that you can realize with this is you can compare it to numerical simulations. So in simulations, you can run structure formation simulations, which show how structure in the dark matter grows as a function of time. I'm sure in large scale structure courses, you may have seen one of these simulation videos, right? And so early on, there is less structure, and then as time goes on, you get more and more structure. So now you don't need simulations to show this, you can see it directly in the maps. So here you can see the structure or the fluctuations that you see are fairly tiny at higher redshift than when you come closer and closer. So indeed the structure in the matter distribution is growing and is something that you can directly see from the. By comparing the growth of this structure to the growth expected from numerical simulations, then you can learn about cosmological properties. So here, for example, how clumpy the universe is. It's constrained by a parameter called S8, which is a combination of sigma 8 and omega matter. And this is the matter fraction in the universe. So what is the fraction of the critical density which is present in matter? That's shown in the x-axis. And from these different surveys, the HSC survey result is here, the dark energy survey is here, HITS is here. You can see we can measure these kind of cosmological quantities and then compare it with expectations from cosmic microwave background experiments. So we can learn a lot about the universe, we can learn a lot about cosmological parameters, we can learn a lot about how galaxies and galaxy groups and galaxy clusters populate their dark matter halos using this weak gravitational lens. So I hope I will convince you that it is quite useful. And with this, I think I should stop here and take questions. And I'm going to just flash this last slide, which shows some of the references that you can follow. So let me stop here and take questions. So people on Zoom, please raise your hands. You can then unmute and tell your questions. Or you can put the questions in chat. I can monitor it. So let's start with the questions in the room first. Yes.
We do see a lot of distortion in electromagnetic radiation. So can we express that gravitational radiations or gravitational waves are better suited for this cosmological parameters, detection or the profiles that are universe present in the universe galactic scales, dark matter survey, dark energy survey.
Right. So there are only very few gravitational waves which have been detected there. Right? So these gravitational waves are influenced by lensing also. But you see, you need many of these things to actually like figure out what is the shear which will be actually acting on this gravitation. So the first thing that people are trying to do is to figure out how the amplitudes of these gravitational waves will change because of this weak lensing phenomena. Okay. Then there are people who are working on strong gravitational lensing of gravitational waves and how the waveforms of these gravitational waves change because of gravitational lensing. And then there are also people, so at IUCAA, so Anupreeta and her students, they are trying to work out what are the effects of microlensing on the gravitational waves. So at different scales, people are studying these phenomena. So one has to keep an eye on the literature as to how gravitational waves can be used. But for the moment, the numbers are quite small. Um, the the signal to noise ratios with which we detect the gravitational waves right now, there are no evidences of differences from what just GR predicts the gravitational waveform should look. But this will change as a function of as we get more and more data and the detectors become more sensitive. Any other questions?
That's the parameter also to justify the age of the universe. Age of the universe.
Age of the universe usually you get with something called a Hubble constant. And if you, so the age of the universe is inversely proportional to the Hubble constant with proportionality constants which depend upon the other cosmological. So omega matter, omega lambda, omega curvature, all of these things can affect, but primarily the scale is set by the Hubble constant. So in order to derive the Hubble constant, you don't use the cleansing measurements directly, but that is more sensitive, or that can be easier to. It is easier to measure if you follow actually time delays in the universe for strong lensing systems. You measure the time delays between different images, and then those time delays are proportional inversely to 1 over h naught. And so that helps you to figure out what the Hubble constant is, and thereby the age of the universe. Yes.
I don't know if I'm getting it right. Can we ever measure the intrinsic electricity of the galaxy using the tangential and perpendicular shear that we calculate?
The intrinsic electricity of the galaxy is hard to measure directly like this. But there are ways to do it. So if you have, for example, spectroscopy, right, then you can take a galaxy and you can take spectra at each and every location. And then you can observe how the velocity field changes compared to how the optical image itself is. Okay. So there are ways in order to reduce or to figure out what the intrinsic shapes of these galaxies are. So there are people who are trying to work on this kind of studies, but it is very expensive because you need to get spectra for each and every galaxy and spectra at different locations, and so it's hard. But people are proposing this because you can, if you reduce the shape noise, which is this intrinsic shapes of galaxies being different, then you can do lensing with even less number of galaxies than are required with just imaging data. And so people are exploring this. These are in the first stages right now. But you can expect more and more such things to happen.
I'm also confused, like how measuring tangential is independent of mass. Isn't it dependent on the gamma 1, gamma?
I'm sorry, can you say that again? Maybe I went too fast. Yes, tell me.
Is it right that the tangential shear and perpendicular shear are independent of mass?
So tangential shear, no, it cannot be independent of the mass model, right? Because
that was
see, tangential and the cross shears, they depend upon, I mean, the shear itself, right? It depends upon your mass distribution because that's good. So your lensing potential depends upon the mass distribution. And these gamma 1, gamma 2s are related to the lensing potential. So gamma 1, gamma 2s depend upon the lensing potential. And so they depend upon the mass distribution. But gamma 1 and gamma 2 are also observers. So if I observe a galaxy, then I can observe an ensemble of galaxies which have been distorted by the same lensing field. I can figure out what is the lensing shear at that location. Right? So gamma 1, gamma 2 are related to the mass distribution, but are observable quantities, which help you to figure out what that mass distribution is. Does that help? I don't know if it helps, or maybe I
At one point you said it is independent of mass model. I don't know what.
Independent of mass model. So
I thought gamma
gamma
T, gamma cross.
No. So here, if you have an azimuthally symmetric distribution of matter, then this holds. And now, even if you don't have an azimuthally symmetric mass distribution, you can show that the tangential shear averaged around circles is related to your mass distribution like this. Now, this formula is independent of the symmetry of your mass distribution. Of course, gamma T depends upon your mass distribution because that's what this couple is, right? But this formula that you see, which looks very similar to this formula, this is very easy to derive for azimuthally symmetric mass distributions. For non-azimuthally symmetric mass distributions, you have to go through something called the divergence theorem. And then the formula that you get is independent of the symmetries of the mass distributions. Whatever mass distribution you have, this will be satisfied. So that's why it's safe.
Thank you.
Yeah, sure. Sorry to confuse you about this point. It's a subtle point, but very good. Any other questions? Okay, I don't see any. Prakash, are there any other questions on the chat?
None.
No. Okay. So then maybe I'll stop here. Thank you. I'll stop.